Okay, I think I'd like to say good evening to everyone. It's almost 6, right? I think we are running late right now. So I'm gonna shorten my talk a little bit, so go faster. Okay. And basically, I think this is a nice city. We see a lot of culture in here. And what I'm gonna do is try to introduce this new system called the polydopamine-laced hydroxyapatite-gelatin nanocomposite for will be used for bone regeneration. And all of my work is supported by a lot of collaborators from different areas, bioengineering, such as chemistry and ADA Foundation people, material science people, and also chemical engineering people. And also like to thank our funding agency from NIH to support us, and also NC Biotech. So to give a brief outline is that I'm going to shorten this background to see why we need this material for bone regeneration, and then starting to talk about what biomimetic material which we are doing, and also talking about some of detail on the processing of the material and mechanical property, and maybe if we have time we talk about a little biomedical implications. Okay, and this is already known. People know that we need, when people has a defect, we need a material to repair, we need a cell to repair. The key is that some of the area and some other area which not shown here, that when the defect is substantial, you need a material which can support the loading. Okay, and currently we don't have that kind of material to supporting the loading. Okay, except the natural bone is one of the best options. In the natural bone, we have a nice collagen structure, microstructure, and has a very good inorganic crystalline binding to those organic material, and they have a very detailed chemical binding. Yeah. And because of that reason, they can provide a very strong strength. For example, from early time Williams, the formula, they calculate the cortical bone by timing the compressive strength to the tensile strength and divide by the stiffness. Then you can get a quality index like 6.83. So the material, artificial material which we like to reach, is something around that number to kind of support the defect. And however, currently most of the material which we are using, especially in inorganic material, for example, calcium phosphate cement type of material, the QI index is only 0.5, and then hydroxyapatite, because it's brittleness of the nature, the QI number only 2.0. So we do need to find some new material which can taking over both organic and inorganic benefit, and then making a strong artificial materials. And this is just showing that even with a natural bone, if you put it into a wrong spot and they still have some growth left, and this patient has undergone the surgery for replacement of joint. However, 10 years after that procedure, the rib continue to grow and become asymmetric. So even with the best material, we still have issues. So there's need to develop new materials. And two options: one is using organic material, however that has immune issues, and the one is using alloplastic synthetic materials. Of course, in this area, a lot of person has pursued different type of approaches. Metallic people are generally used, but they are not resolvable. They cannot be long-term use. And polymer materials, although they are creating a lot of very nice detailed microstructure, even nanostructures. However, in personal communication with the NIH folks, it's a little bit frustrated at this moment because the material itself is not strong enough. So although there's a lot of beautiful publications, the translational value is still very limited. So we still have to looking for some composite materials. And here's one of the example of ours. We're using the composite material, using hydroxyapatite-gelatin, and creating a porous structure. And if you compress this material, you'll get the loading curve like this. But however, if you're taking collagen and you compress, you will get this number, which means that there's not enough stiffness to support the loading. And because the skeletal bone is functional as the mechanical supporting tissues. So we do like the material to have this kind of mechanical properties. In the past, almost more than 10 years ago, our group has developed biomimetic hydroxyapatite-gelatin nanocomposite using co-precipitation processing. And the material allow us to create, this is, you can see the dark is a nanocrystal hydroxyapatite. And they formed as a plate-like material on top of gelatin matrix. And by taking out those matrix, you can look at the TEM, and this is going to show like a TEM in here. The schematic drawing of the material structure is like this. Okay, so you can see the unstructured gelatin and deposit with a hydroxyapatite crystalline. Okay, yeah. So during the past 10 years, our group has been focusing on how to making this material into a best composite material, which has enough strength to support the defect and also has a better biological response. So here is showing that in the past we have looking why this material is interesting, because the gelatin has an effect on the mechanical strength. Compare the material with the gelatin without gelatin. You can see when it forms a composite, the mechanical strength is much higher compared to the pure hydroxyapatite. And our hypothesis is that this system should derive a composite which can be molded into a 3D porous scaffold and used in the critical size defect for stem cell mediated bone regenerations. So there's a few objectives in here we are working on is to make sure we can, the composite system can mimic some chemical bonding like a natural bone, and to create something like interneck work similar to the collagen fibers. And then the second thing is to make sure we can match some of the quality index of the cortical bone, and then to looking at the biological properties, how they can promote osteogenesis. So in the past, we have been developing several different cross-linking agents, and the first one is sol-gel reactions, which allow us to creating a weight chemistry reaction. And however, the reaction is a little bit slow, so it's not very practical. So we add another reaction called the porogenic reaction, which to adding the calcium silicate into the system, which actually shortening the setting time and make a material more resistant to the wet conditions. And most recently, we add another reaction, which is the main topic of today, is dopamine into our system. Because dopamine is dopamine protein present in a lot of like food, like a muscle. Okay, so when they attack to the rock, they're using majority of the dopamine protein there, and this was published by Messersmith in 2007 in Science, and itself from dopamine to be polydopamine is a very simple procedure. You just change the pH value, and it's automatic polymerization. So we find it's probably a useful chemical reaction, so add into the system and doing some testing and find out it is helpful into our system. So this is when we started using this dopamine into a system. In the beginning, we use the dopamine, but we make our material in a room temperature. And we find that the mechanical strength was not increased, instead it's dropped from the 2 to the 3, which is a dramatic drop. And we will spend about a year to figure out why it happened. And then finally we find out that in our system, we do need to suppress the sol-gel reaction and then let dopamine reaction going through first. So therefore we use the processing in number 1, which increase the mechanical strength and also increase the toughness of the materials. And in this part, we make two hypotheses just to make sure our hypothesis using a differential temperature is helpful on the systems, and also the material cells is homogeneous. So by doing that, we run some thermal processing in here. For example, in this case, we run two different reaction. one at 20 degrees C, one is at minus 20 degrees C, to looking at Soldier reactions. So basically you can see it's in a warm temperature, the Soldier reaction goes very fast, okay, within about few minutes, it's going fast. Under the cold reactions, the Soldier reaction was suppressed, so it's become very slow, okay. And on the other hand, when we look at the polydopamine reactions, at 20 degrees versus minus 20 degrees, there's almost not much difference in terms of reaction trends. So just by using this differential reaction, we developed the new systems. And in here, with the core processing, we can see that we can schematically draw in that the polydopamine has become internet working, interdigitated, and provide a better mechanical strength. In the core reaction, they don't provide the internet working. And then we did some optimization to find out what's the best ratio in our current composite. It's about 40% of hydroxyapatite-gelatin particles and about 20% of calcium hydroxide, and which require about 25 to 40% of dopamine silence composite. And the final composite material, which we can show in here, our current material is about 5 for the quality index, which is getting closer to the cortical bone. Okay, and the part of the reason is because we increase portion of compressed strength and also measure years. And besides that, the system also allows us to do the computer design, okay, to design the scaffolding. And what we did now is using the indirect scaffolding method, which means we're using the polysulfonate, okay, to design negative mode, and then we infiltrate our composite fluid before it's set, and then quickly remove this polysulfonate, which just using the acetone solution, and within about 3 minutes it would remove the material. So we can start to design a different type of geometric and prosthesis. So let's all talk about the mechanical, physical advantage. How about biological? So we have to make sure the material can be used for the tissue regeneration. So we look at some attachment assays, viability test, and also looking at some differentiation effect. And also finally, we look at some dopamine effect on it too. So in those biological testing, we're using the MC3T3 pre-osteoblast, and also we're using some rat isolated bone marrow MSC. And then we culture those on the coated dish or with a positive control, non-coated dish, and then with a negative control, which is no cells. And we're looking at some proliferation assays and also differentiation assays. So here is one comparison. In our system, when there's no dopamine inside it, you can see the cell is become sporadic and more spindle type. Once we add the dopamine, which forms polydopamine in the systems, and our cell has become more stretched, and the proliferation also increased. And also for differentiation, okay, in here there's only material, there's no cell, okay, so you can see some material effect on the staining as well. This is the arizona red stand for the mineral nodule. But in the second row, which is cell only, which using the normal petri dish, and you can see normal mineralization nodule. If we coat it with our material, you can see the mineral nodules start to form very early, okay, and also covers the entire dishes. And we further look at SEM and TM to confirm those nodules. So basically, in the SEM, you can see the nodule on the surface of collagen fibers, okay, and TM, you can show those H band is disappear and deposited by the nail crystals. And also in the MSC data, we can show that when we add the dopamine into it, it's start to form the nodule or bone mineral nodule. Without dopamine, it's become very slow. Okay. finally, I want to talk about the new system we have, and it's very interesting. When we add the dopamine, it's not just increasing the mechanical strength. We also find that it has a helpful for the osteogenesis, and we're starting to wondering why it's happened and how it's happened. So we're kind of in the process at this point to find out the mechanisms. So we have tested some of the cell line like MC3T3. And we find they do contain all the dopamine receptor from 1 to 5 on the bone cells, and which has become very interesting. And so we suspect that maybe some of the leaching the monomer dopamine has some stimulating factor on the bone formation as well. And okay, and this one is showing that when we put a growth cell under the growth medium and compare with the growth medium plus dropping the dopamine into the culture medium for 50 micromolar, and we find that just in the growth medium, it's starting to form the nodule in these conditions. In the osteogenic mediums, it's increased just slightly, not as dramatic as the growth mediums alone. And right now we are still doing the animal testing, okay? And you can see this green is our scaffold material, which means we contain the cortical portion and also porous mesh inside here. And we can print the entire system and design different structures we need as needed. And we can design different porous size in there to do that. And this is from the rats. Okay, the mandible we do osteotomy, we completely cut off the mandible and then put the prosthesis and then seed it with the MSC cell in there. I don't have final data for you because we just started this animal part about 2 months ago, and then currently we have 3-5 animals running around. They are still kind of intact in there. Okay. So to summarize very quickly, we adding this dopamine, we increase our compressive strength. So it's close to the natural bone. It's reach about 70% of the compression strength. And for the fracture strength, it's reach about 60% of natural bones. And now we can do a computer design for the different scaffolds, and its material seems to be biocompatibles. And some of the polydopamine can substitute of a soldier reaction component in there. And there's seems a connection between the neurotransmitter and the bone regeneration, which already been pointed out by the Cliff in 2009. And they have mentioned that there's serotonin receptor on the bone cells. Okay. However, they haven't looking at the dopamine receptor. So our next is try to do making some functionalized polymer, which has a catechol, which is kind of dopamine, the main function, has catechol on it. By doing this, we hope to increase the toughness of the materials. So kind of very quick. So thank you for your attention, especially this late. Okay. Yeah. Okay. Any questions? Yes, please. Thank you.
So the question is that dopamine, as everybody knows, is the transmitter and most of working in the neuron.
Right.
So right now you change the temperature, the dopamine becomes like the bioengineered material.
Yes.
So how much the dopamine and the cell biological activity still remaining in your bioengineered material? Do you have any idea?
Thank you. That's very good questions. We are still looking at the leaching study. Okay, we have very little data on that. The leaching components at the micromolar level, and that's why you see our cell testing is in the micromolar level. Most of the dopamine has been converted into the polydopamine in the systems. Once it's converted to polydopamine, it no longer has the dopamine effect. However, there's quite a few articles has been published. They also mention polydopamine also increase the cell adhesion. They can increase the integrin reaction with the cells. So that's another advantage with the polydopamine.
Biological activity only lasts,
Yes. Yes, but they instead provide the adhesion. Okay, and very interesting is monomer dopamine, how it's going to affect cell, and that's our. I have a few people are working on this area now. It's very interesting. We also find something to do with optineling, okay, which is kind of autophagy of the system from the dopamine effect. So there's quite a few stuff ongoing right now in there. Okay, yeah. Okay.